Buenas tardes a todos. Good afternoon, ladies and gentlemen. Quizás es mejor esperar 2 minutos a que se siente todo el mundo y se tranquilice la sala. Bueno, si ustedes hacen el esfuerzo o el ejercicio de buscar en algún texto básico la definición de la palabra química, o incluso mejor que en un texto básico, todo el mundo lo hace ahora mirando Wikipedia o cualquier otra en Google, ustedes encontrarán, más o menos hablando de forma simplificada, que la definición de química es la ciencia que trata de cómo los átomos en determinadas circunstancias pues les gusta estar juntos, forman uniones que hoy llamamos enlaces y dan lugar a entidades un poquito más complejas que llamamos moléculas y que son estables en determinadas circunstancias. También encontrarán o podrán leer o ver en la pantalla de televisión o de Internet que también la química se encarga de estudiar cómo estas moléculas se transforman unas en otras mediante determinados procesos que hoy en día llamamos reacciones químicas. Sin embargo, hoy en día, y gracias a los trabajos de Marie Lehn, del profesor Marie Lehn, sabemos que hay química más allá de las moléculas y más allá de los enlaces covalentes, que son los enlaces entre los átomos, en particular de la química orgánica y de la vida. Esta nueva química, que hoy en día conocemos como química supramolecular, está basada en la unión o la formación, mejor dicho, de entidades complejas entre moléculas, formadas por diversas moléculas, no mediante la formación de enlaces químicos, sino mediante sutiles interacciones intermoleculares, que además, en la mayoría de los casos, son dinámicas, es decir, que cambian con el tiempo. Este nuevo concepto de química ha pretendido extender la química hacia campos tan distintos como, por ejemplo, los procesos de autoorganización, el famoso self-assembly, que tanta importancia tiene hoy en día en las nanotecnologías, hacia los procesos de reconocimiento molecular, que son tan importantes en las ciencias de la vida, hacia la química adaptativa, etcétera, hacia un montón de nuevas posibilidades para la química, y quizás de forma más general, como le suele gustar decir al profesor Marie Lehn, hacia contestar quizás, o por lo menos ver el camino de contestar, una de las preguntas más básicas quizás de la ciencia, y es «How does matter becomes complex?», en palabras del profesor Marie Lehn, es decir, cómo la materia se hace cada vez más compleja y se forman estructuras más y más complejas. Es para mí hoy en día, hoy en particular, un gran honor y un gran placer presentarles a ustedes al profesor Marie Lehn, Premio Nobel de Química, en 1987, y hoy en día quizás yo creo que podemos ya decir que visitante habitual de San Sebastián. Yo creo que tanto la biografía, la pueden ver ustedes en Internet también, la biografía como la personalidad del profesor Marie Lehn responde perfectamente al título que da nombre a estas jornadas, la pasión por el conocimiento y, en particular, por la aventura de conocer. Y quisiera yo extenderme y decir que no solo por el conocimiento científico, sino también por el conocimiento en general, en todas sus facetas. Ya desde sus primeros pasos en la escuela secundaria, Marie Lehn se siente súper interesado por la música, una de sus grandes pasiones, además de la aventura científica. De hecho, su padre era organista del pueblo donde vivían, en Alsacia. Después, cuando va a la escuela, estudia lo que hoy llamaríamos clásicas o humanidades, es decir, estudia un perfil con griego, latín, alemán, inglés, literatura francesa, filosofía, aunque también se sentía atraído por las ciencias experimentales. Al entrar en la universidad duda entre la filosofía y al final se decanta por la química orgánica, según dice él, influido por las clases de un profesor Guy Ourison o algo así. También sus primeras actividades en química son muy multidisciplinares. De hecho, en la tesis doctoral profundiza en la técnica experimental de RMN, pero después, cuando va a Harvard de postdoc, entonces participa en la síntesis de la vitamina B12, pero a la vez hace cálculos computacionales de química cuántica, es decir, que adquiere una formación muy multidisciplinar en ciencia y en el conocimiento en general. Yo creo que es esta formación multidisciplinar la que le permite, cuando ya vuelve a Estrasburgo y forma su propio laboratorio, empezar los desarrollos de la química que le conducen a lo que hoy conocemos como química supramolecular y al premio Nobel. Desde entonces, Jean-Marie Lehn ha extendido sus actividades en muchos campos y ha recibido, por supuesto, numerosos premios y distinciones que serían demasiado largo y prolijo contarlos aquí. Sí quisiera acabar esta presentación con una reflexión propiamente personal. Yo pienso que lo que le ha permitido a Jean-Marie Lehn ver donde otros habían mirado y no habían visto nada, porque como suele él decir, la química supramolecular estaba allí, es precisamente esa formación multidisciplinar, y eso no solamente en los aspectos científicos, sino también en muchos aspectos del conocimiento. Es importante resaltar eso hoy en día, en una etapa en la que estamos involucrados, en la que normalmente tiende a que los objetivos de la investigación están muy predeterminados, los currículos de los estudiantes están muy predeterminados y, de hecho, hemos abandonado de alguna forma el interés por las humanidades en los currículos escolares y por otros aspectos del conocimiento que no son el conocimiento científico puramente dicho, pero que yo creo que son muy importantes a la hora de desarrollar el conocimiento tal como Jean-Marie Lehn nos ha mostrado a lo largo de su biografía. Señores y señoras, es un gran placer introducir a Jean-Marie Lehn.
Good afternoon. It's nice to be back here in San Sebastian. I've been here many times. It's always enjoyment to see things developing here. This is a special occasion, on one hand, because we celebrate the 10th anniversary of the DIPC. Pedro, your child, one of your children, yes. And also to participate in this very special meeting, which has a very special title. Passion for knowledge. 2 words of great importance. Scientists have to be passionate, rationally passionate, but nevertheless passionate. So I would like to sort of present you chemistry, an area which often is considered as not interesting. People always tell me, I never understood chemistry, I never liked chemistry. So let me show you that after all, you should like chemistry. And I put it in a very broad context, which, if I give the beginning of my title, is usually very attractive. From matter to life. What a title. Everybody comes to see that, I guess. You can make movies, you can make lots of things. And then you come chemistry. Well, really, chemistry? Yes, chemistry. So let's see where we start. We had magnificent lectures yesterday on materials, on biology, and the progress we can foresee. Just now on the intimate world of quantum physics. We're now going to step up a little bit. What goes on underneath is of course very important, but we take a level of somewhat higher complexity where the processes which go on concern us very directly. And we start here. Long time ago, 13.7 billion years, as cosmologists tell us. The beginning, as we heard also this morning when we were discussing with Frank Wilczek, after the Big Bang, was so hot, no chemistry. Physics. Physics is a rule. There is no chemistry. It's much too hot for any chemistry to occur. But the universe cools down. Particles form, particles get together, they make atoms, and then atoms get together and chemistry starts around here. These atoms get together, make houses, molecules out of the bricks, This becomes more and more complex by procedures, by processes we have to try to understand. And after some time, it gets complex enough that a process of, after chemistry, a new process sets up, which leads to living organisms. Life. Biology starts. But that's not the end yet. Biology evolves and generates ultimately, at least at the present stage, and on our planet, an organism which is able to think. Before I continue, let me just point out one very important thing. If you look at this drawing, you realize that it will not stop here. The universe will not stop evolving, and we cannot be considering ourselves as the end of evolution. The universe will continue. We will be part of that evolution. We may have an influence on that evolution. Things will change. We don't know how, but they will change. That is sure. Human beings are not the end of the evolution of the universe. So, this matter in this universe, cosmologists tell us that 95% we don't know exactly what it is, dark matter. 5% is the visible matter, the one we are part of. And this is the matter that matters. Not that the other one is not important, but for us, that's the matter that matters. So we try to define what happened looking at two parameters, information and complexity. And this evolution of complex matter starts with divided matter, particles. Particles get together, they condense. After condensation, there must be some organization setting in. So matter becomes organized. Organization, if it gets more and more complex, I guess say again by processes we don't yet know, but they must be there because it happened. Living matter, thinking matter, and maybe something else. I can't tell you what can be up there. It's very difficult to think beyond your own thinking, but you cannot exclude it. So the evolution of matter looks like it's a sort of I wouldn't say Darwinian, because Darwinian is just biology. There's something else. Such a pressure of getting more and more complex. So what is then the big question we can ask? Physicists study the laws of the universe. We just heard that. Biology studies the rules of life. So what is the big problem in chemistry? What can be the big question chemists can contribute to? Not just making molecules and materials, which is very important, but in what context? What type of context is there where the big question is asked from chemistry? What is it? How does matter become complex? From the elementary particle to the thinking organism? And is there something beyond which can be evolved, which can be created? Physics is one pillar, the laws of the universe. Biology, the rules of life, and chemistry builds the bridge between the two, the bridge towards complex matter, of which biology is the highest expression. But biology is based on molecules and therefore on chemistry. So that's a big question, and we know the answer. You say, oh, come on, what is he telling us? How can he know the answer? This would be in all newspapers, in Time magazine, everywhere. Oh, sure, we know the answer. Doesn't mean we understand the answer, but we know it. What is the answer? Self-organization. It happened because the constitution of the universe, the laws of the universe are such that it is possible. And we are sort of a tautology. It is because we exist that it is possible. But that doesn't tell us how it is possible, and that is where chemistry has to come in. One can consider self-organization as a cosmic imperative. In other words, the universe cannot avoid getting self-organized. That's something one can discuss. But one can say that indeed the universe has this structure, has the features which make it self-organized and lead to more and more complex states. Now, we had this morning also in the discussion we had with students from Frank Wilczek that there are several forces around in the universe. One of them, gravitation, is this force which led to the organization on the grand scale, the scale of the universe. And if you read books by cosmologists, they tell you that gravitation has structured the universe by acting on slight inhomogeneities in density, in expansion rate, at very, very early times. This is not what we are talking about in chemistry. It's very important, but it's not our business. What is our business is the other type of forces, the electromagnetic forces. What they do, they bring these bricks of the universe together, they make them connected, they generate structures, bricks get together, and different types of combinations. They operate on that, and some combinations happen for some reasons, that they happen at the right time, at the right moment to get together and to lead to something better than something else. So, self-organization of non-living and living matter is a result of electromagnetic forces acting on the bricks of the universe. And we come back to what these are. One very important thing to realize is that we do not yet know how life evolved, how it came about. But it is clear that before life existed, there must have been a prebiotic evolution which was purely non-living. In other words, you cannot get to the level of complexity of living systems if you don't have a complex evolution before that, which leads to stages of higher and higher complexity in their organization. So, there is a prebiotic, chemical, purely chemical evolution. One can then define among these areas created by the curiosity of human beings trying to understand what we are doing here. What is the universe around us? We have divided this up because we cannot do everything only 24 hours a day, 7 days a week. So we have mathematics, we have physics, we have chemistry, biology, psychology, sociology, and all that. And chemistry deals with the structure of matter, what it is made of, how it is built together, and very importantly, the transformation. One thing is how it is built, but how can you go from one set to another set? This is probably the most creative part of chemistry. So, people have looked at that, and just a very quick panorama of some historical points. I could have chosen other ones. I chose those ones, but just because they are milestones. Minus 500, Empedocles proposes that what's around us, trying to sort of figure out what it is, okay, there's fire, there's air, there's water, there's earth. We combine them, it gives properties, dry for fire and earth, hot for fire and air, humid for air and water, earth and water giving cold. It's primitive, but okay, it's an attempt. But at the same time, another philosopher already had the right idea. Democritus proposed that the universe is made of things which cannot be made smaller. Particles, atomos, you cannot make them smaller. And these are the bricks. Now, this doesn't mean that Democritus has discovered atoms. For being a scientific fact, you have to prove that it is correct. But the idea was correct. And it took a long time to prove that indeed atoms is what the universe, at least our matter, is made of. So let's just give a few points. Accumulating this analysis of matter, people noticed that there were some ratios between substances, and they give them these strange symbols, which you see here. This is about 1718, that's how it looked. These strange symbols were given to things like acids, like mercury, like gold, like silver, zinc, and so on. All right. Looks like sort of a magic type of thing, something which astrologists would look at and show you this is your sign and so on. But of course, it was a bit chaotic. What do you make some sense? Can you make some sense out of it? So these things continued, when found more and more those things which cannot be reduced further, until a number of efforts done by a number of people eventually came up to a real nice organization of what is called the elements, and that was due to Mendeleev. Mendeleev in 1868 published a table which was incomplete, which organized the elements known at that time in this table, a very simple table, which is now like this. That's the full one. Mendeleev had, at that time, it was incomplete. There were holes, and he had the courage to say, someday we will find something to fit in these holes, and they were found. Now, this is, for me, and I would like to insist on that, one of the glories of chemistry. If you look at this table, this is full. It shows you all the bricks, the visible universe, our matter is made of. There's nothing else from the planet Earth to the end of the universe to build up matter. If there are living organisms somewhere else, I'm convinced they are, they must be made of this. There's nothing else. That is fantastic. I think I usually say to people, if you take a photograph, hang it over your bed, and look at it every morning. Because that's really one of the major steps science has taken and shown to mankind what matter is made of. Now this is the bricks, but you have, and they build the houses, the molecules. But then you have to transform this, and you have to learn what are the laws for taking some of those bricks, putting them together in reaction, as one says, and transforming that into something else. This was first understood by Lavoisier, when he said, rien ne se perd, rien ne se crée, tout se transforme. The elements come in, they get out on the other side, but in a different arrangement. And this is the law of chemical reactions, without which you cannot do any chemistry, you cannot understand any chemistry. So, after having learned about the composition of matter, the question came out, are there connections? In other words, you have bricks, but you would like to know how they are connected. If you build a house, the brick, a given brick is sitting at a given position. So how can you connect? And people realized that these things were connected. And so in the mid-1860s, a number of representations of these connectivities were proposed, one by Wurtz, one by Kekulé, and the closest one to the present day one is one by Loschmidt in Austria. And so one had a better and better sense of the connections between atoms. That's a major step, but it's not the end. Because after all, composition is one thing. Connectivities between the bricks is the other one. But if you have a house, it has a shape. And this was then in 1874 proposed by two people that indeed molecules have a shape, by Van 't Hoff and Nobel. In 1874, they published, same year, this idea that molecules have a three-dimensional shape. They have an architecture. They are not just connections. This is because between the atoms there are given rules for positioning them around each other, and that leads then to the shape of the molecules, stereochemistry. The last property I would just like to mention, which I cannot avoid, obviously I don't want to avoid, because it has to do with something which is characteristic of living systems. Many molecules in living systems have a property which is chirality. They are like a left hand or a right hand. Usually in a biological system, they are not both left and right. Either we are left, our molecules are left of the left-hand type or the right-hand type. This is just by chance. We could have been built completely differently. We would look the same, but the molecules would be different, would be left-handed or right-handed. But this property, which was recognized by Pasteur on studying tartaric acid, the acid you find when you have a wine bottle and nice crystals inside, this is tartaric acid, and this was really the sort of the emblematic type of substance which led to this idea of molecular chirality, left-handed or right-handed. So atoms are the bricks, the molecule is the house. And so chemists have tried to learn over the years how you can organize matter, how you can take these atoms, build them into molecules, understand how you can do it, which processes, and this has been led to an enormous area, the area of molecular chemistry. Two milestones. In 1828, a German chemist, Friedrich Wöhler, made urea from a compound which is called ammonium cyanate. Now, what is important about that? First of all, it's a synthesis. It's transforming ammonium cyanate into urea. Second, urea is in our organism. It's a substance contained in living organisms. At that time, one was thinking that you cannot make in the laboratory a substance contained in a living organism without the help of something living. Wöhler, by making it in the lab from ammonium cyanate, which is a non-living, which is not in a living organism, showed that this vital force, this magic force, does not exist, and between objects which are part of what we call non-living matter and objects, molecules which are part of what we call living matter, there is no difference in nature, in essence. That was very important, not just scientifically, but also in the conception of the world. 150 years later, we heard about, I think in the introduction, we heard a little bit about vitamin B12. The combined efforts of two groups, one led by Robert Woodward at Harvard, the other by Albert Eschenmoser at ETH in Zurich, realized the building up by progressive steps from the bricks, carbon, hydrogen, oxygen, nitrogen, some phosphorus, a little bit of cobalt, of this very complex molecule called vitamin B12, which exists in our organism. I participated in that. That's my part here. And I like to show that also to especially students. When you are scientists, you contribute a stone, a small stone or a big stone, but it's your stone. And I think in this B12, this is my stone. It's part of it. I am only one in 120 or so co-workers who have been able to make that. But it's a common effort. It's building this enormous edifice, which is called science, and here chemistry in particular. Now, this is molecular chemistry. Then you can come to the point and ask, so what else should we look for? This looks like biology. In some ways it is biology. But I would like to make you aware of one thing. This is a cancer cell. These two things are killer cells. The killer cells, we have them in our organism. They run around. They have to find out if one cell has gone wrong, and they have to destroy it. How do they know which cell they have to destroy? What tells them? If they make an error, they destroy a good cell. Not good for you. If you don't find the bad cell, it's not good for you either. So something must tell the killer cells that the other guy is a cancer cell, and I have to destroy it. What is it? This is a white blood cell. It's colored artificially in rose with blue dots. Blue dots are the HIV virus. When the HIV virus collides with a white blood cell, it has some knowledge that it has reached the goal and can now infect. How is it possible? How does the virus know that it has reached the goal? How can it get in? So what these examples tell you, and could give you, of course, many, many others, is that something must happen between the killer cell and the cancer cell, between the virus and the white blood cell, which tells the two partners that now the next step is starting. Here, destroy the cancer cell. Here, infect. And this thing which happens must be between the bodies. And these bodies are defined by a membrane. And this membrane is made of molecules. Therefore, the molecules in the membranes must talk to each other. They must say something to each other. They must sort of touch and do something. And this process is, of course, happening between the molecules making up the cells and not inside. In other words, there is a chemistry to be developed which deals with what happens between molecules. And that is the chemistry which one can call supramolecular chemistry, which we have been working on for many years now, which is to use the forces which link together, which make molecules interact, to let them touch each other and feel each other out, and then get information from what that partner is and whether something can be done with that partner. And so we go from molecular chemistry to supramolecular chemistry. The most important process, you have already understood it from what I said, is that molecules can recognize each other, molecular recognition. Now, how can you define this recognition? Let's simplify it. It has to interact. Without interaction, they don't talk. There has to be some kind of glue which holds them, which tells them something. And very importantly, there is no recognition without information. So when molecules interact in this very selective fashion, like when you get a vaccination where the antibodies interact with the antigen very selectively, like when you make a drug, you want it to interact with the biological target very selectively, if possible. So there must be some kind of information in the molecules, which most simply can be represented by an image which was already given in 1894 by Emil Fischer. At that time, he didn't talk about molecular recognition, but he had this very right idea that for an enzyme, a biological molecule, to operate a transformation on its substrate and generate the products, they must fit together in some way, and he had a very geometric idea, but not wrong, just incomplete. They have to fit like Schloss und Schlüssel, like a lock and the key, shown here. They have to fit together, and when they fit, this is the fitting, this is sort of the geometric complementarity, which we now know has also to be complemented by an interactional complementarity. But the basic idea was there, and later on this developed into, much more recently in the work we have been doing in the last 50 years, into what is called now molecular recognition. Here is Emil, one of the greatest organic chemists around. We're very happy. He got his PhD in Strasbourg, 1874, when we were part of another country. That's how geography and history changed. Now, what is a very typical example, maybe the most important example of molecular recognition and information? We all, as we are sitting here, depend on a genome. And all living organisms, plants, bacteria, elephants, tomatoes, depend on their genome. What is a genome? A genome is a long string of chemical groups. 4 letters, just 4 letters. These 4 letters are A, adenine, G, guanine, T, thymine, and C, cytosine. You must realize that these 4 chemical groups, this, and this, hooked together in a very long strand, define all living organisms. All the information which allows all living organisms to transfer their genetics, their information, is written with just 4 chemical groups. One very interesting thing, since I have started with the universe, is that let's look at one letter, adenine. What do we see? A little bit of chemistry. Adenine, this one, can be put together like a Lego set by taking 5 molecules of HCN. That's a molecule, very toxic, cyanic acid, hydrocyanide. And when you take 5 of those, you can put them together to make that. What does it mean? That exists in the universe, in the interstellar space. So, nothing special. Nothing special. 5 HCN make adenine. You add some water, you get guanine. You do some other transformations, you get thymine, and you get cytosine. In other words, the 4 letters which make the information of all living organisms can be deduced in simple ways by a rather trivial chemistry from very simple molecules. That makes us a bit modest, I would say. Now, you store the information, but you have to do something with it. How do you read it? How do you process it? Very simply. The information is this molecular group, AGTC, these letters. This is molecular. These are molecular groups. But they interact. Here, these dots in the green rectangles indicate that the interaction can be by 2 touching points, 1 and 1 here, or 3, 1, 1, 1. Adenine and thymine interact by 2. Guanine and cytosine interact by 3. A binary process. Very simple. Cannot be simpler. 2, 3, 2, 3, 2, 3. You have a long string, and you read out 2, 2, 2, 2, 3, 3, 2, 2, 2, and so on. So, the writing of the information is in itself using a very simple way of coding, And the processing of that information is using a very simple binary system, which is very easily understood on chemical basis. So one can claim that chemistry is not just the science of the structure of matter and its transformation, but it's also an information science. In other words, molecules are not stupid, so if I may say so. They have information, they process it by their contacts, and DNA, and all the processes occurring in the storage and reading of genetic information is there. Molecular storage, supramolecular reading and processing. So just one example of how you can handle that. And this was the simplest we started with to try to understand molecular recognition. Of course, molecular recognition always existed. It happens in our body all the time. All the processes occurring in our body, as you are sitting here, are based on molecular recognition. All of them. Now, how can you try to understand how to do it? That's to do what science can do. You have an idea, you test it, and if it works, you hope that you have understood something. So if the receptor has this shape, the cavity, the key, the lock, then you have keys, and obviously the red key is the one which fits. And so you try to select simple, at the beginning, simple keys, and you build the lock for them, or you build the lock. You build the keys for the lock, one or the other. You build the lock for keys or the keys for locks. And this we have done many years ago now with this very simple objects of chemistry, which is one column in the periodic table of Mendeleev, which are called the alkali metals, lithium, sodium, potassium, rubidium, cesium. One of them, you know, every day you use it. Sodium chloride, kitchen salt, that's sodium. Potassium is very important, and the reason I became interested in it is that the change of sodium potassium across nerve membranes is the propagation, carries the propagation of the nerve influx along the nerves. This is a very basic process for all of us. When I do that, this is running, all this information running down, telling the muscles, you now extend or you contract. And this is sodium potassium. So there must be, in the membranes, there must be molecules which are able to distinguish between a sphere and another sphere slightly larger. So let's apply Emil Fischer's lock and key. In other words, in more general terms, molecular recognition. And you can then try to use, if you can bind or transport these ions through membranes, like in the nerve, in the case of the transfer of nerve information and influx, and you would like to perform spherical molecular recognition. Here are the substances we built now many years ago, 1968. You make molecules which look like locks, which have a hole, which have a cavity of spherical nature, and which you adjust. You make it small, you make it larger and larger and larger. These chemists can do that by building these molecules up from the atoms which constitute them. Carbon is black, hydrogen is white. This is just, of course, a convention. Red is oxygen and blue is nitrogen. The smallest one fits lithium. The larger one fits sodium. This one fits potassium, which means that indeed you can sort of tailor-make your molecules for having the shapes in the cavity, the lock to have the shape, just to select for the correct key. Of course, this has been developing enormously, and many studies have been done to try to understand better and better for more and more complex locks and keys how you can do that. Just one very important thing is that in terms of applications, one most important application is, of course, if you want to design a drug, a biologically active substance. What it is, a drug we are taking is in principle a key for a biological lock, to activate it or to inhibit it. And you would like to make it as specific as possible, so it just goes to the target and not somewhere else. And this doesn't mean that drug design has been not developing before that, but understanding the basic principles of molecular recognition is absolutely necessary in order to be able to understand how to build efficiently drugs. We have been working on that quite extensively, and I haven't time here, but we have developed a drug which binds to hemoglobin in our blood, which makes it release more oxygen than usual, and this drug has very important applications in cardiovascular disease as well as in cancer. and is now in stage 1 clinical trials. Maybe when I come back someday to San Sebastian, I can tell you more about it. Another thing which happened is that we have used some of those compounds for medical diagnostics and one for gene transfer. Just very quickly, 2 slides. One of those cages, but modified one, into which an ion from the periodic table of Mendeleev has been introduced, which is called the europium ion, which has a property of having a strong red fluorescence when it is in the cage. This is like a little light bulb, but with red fluorescence, and you can hang it onto some kind of an immunoagent, on an immunomolecule, and develop medical diagnostics using immunoanalysis. And this was done by CISBio International, thanks to the very, very profound efforts of Dr. Jamatis. The other application has to do with the ability to lead a compound through a membrane. A membrane is what defines our cells, isolates the cells from the surroundings, and regulates what goes through. Now, when genes are deficient, like in certain diseases, you might hope to be able to correct for that by introducing the correct gene into the cell and have it expressed. In other words, you have to pick up a piece of DNA of a gene and let it into the membrane and then let it be expressed and generate the correct protein. So the idea is to build synthetic vectors which will bind the DNA and help it to go in. Of course, then it's very complicated. I can't go into all the details. It has to go to the nucleus, has to be expressed and give a protein. And just give you an example. At the beginning, you use what is called a reporter gene, a gene which gives a product, a protein, which is easy to see. For instance, it's blue, or it gives off light, it's luminescent. And here, just an example of some of the things I've been doing. All the cells which are blue here are transfected cells. So it does work. It doesn't mean that the problem is solved, because the compounds which do this have to be non-toxic and all that. But gene transfer for gene therapy using artificial vectors is certainly something to consider. And even if it's not for gene therapy, in biotechnology, the ability to introduce a gene into a cell and let it be expressed is, of course, a very important property. Now, let me go to this next step, which is how does this lead to being able to progressively decipher self-organization. If you understand better how molecules get together, how they handle their way of adjusting, of organizing themselves, you may hope to use this build-up and this way they interact for setting up systems which will spontaneously, but in a controlled fashion, lead to a given final compound. In other words, bricks which will get together and spontaneously organize, but in a controlled way, on the basis of molecular recognition. One example, which immediately will sort of show you how this can happen, is of course a biological one, but as you will see, it's purely chemical, so to say. A virus, let's choose the simplest, one of the simplest viruses, the tobacco mosaic virus, which is a virus found in tobacco plants. It's an object which is made from 2,130 bricks. And these bricks have the shape and the surface interactions such that they get together and spontaneously interact with each other and form progressively a cylindrical type of tower. And in the middle of the tower sticks the RNA of the virus. And you would say, this looks like magic. How can this happen? It's not magic. In fact, it is rather simple chemistry. Let's say complicated chemistry, but not complex. Complicated meaning it's a complicated molecule, it has many interactions, but the way they get together is something, if you know the structure of the brick, then you know exactly how they will fit together. And this is what happens. They get together on the basis of the physico-chemical interactions occurring between the bricks, which have a given shape and given points of interaction. This is the simplest form of self-organization. Of course, that's only one step, but it shows that one can perform this type of system and can set up this type of systems. Let me just give you one type of example. Many people have been studying over the last 15 years the possibility of synthetic systems. That means systems made not from molecules found in biology, but from molecules you design in the lab to make them in such a way that they will generate a given entity. I want to stress again the fact that this building up of a virus, spontaneous, again points out and stresses the fact that chemistry is an information science in that respect. It looks like a program. The information is present in the bricks. The reading is by touching the correct way, and if it's not the correct way, they will deassemble and form the correct one. So the information is in the molecules. The reading is by the contact between the molecules, and you can even define what you might call an algorithm reading, which is the way in which this interaction occurs, this way or this way, the basic patterns of interaction. And so this stresses this fact that you can build up chemical systems, that chemical systems contain information and they behave like a programmed system. Just sort of illustrations, pictures. Suppose the bricks are an organic molecule. The cement which will bind them together, will cement them together, is a metal ion or zinc or cobalt or nickel. If you design correctly your bricks, and if you choose correctly your cement, you can generate spontaneously architectures in a controlled fashion. Spontaneous, you just mix, but it's controlled by the way it's built and the way they interact. This is just an example of helices, which have nothing to do with DNA, which are entirely synthetic. In other words, the molecules are made in the lab, and the way they hang together, you don't see much here. You see a little bit coming out here. 3 middle lines. This is a double helix, and that's a triple helix, 3 strands wrapping around each other and held together by 3 middle lines. These are, in fact, 3 nickels. These are 3 coppers. This is only to illustrate that it is possible to generate artificial double helices which have nothing to do with DNA. It's just a game, so to say, but it shows that you're able to do it. What about making objects which look more like some kind of electronic device? This, if you look at the right here, you would say, oh yeah, that's a grid. This is something which has wires. It has red dots, which are connections between these wires. And indeed, you can design molecules which look like these bars, which have these slots into which these red dots can fit. And then they do assemble by principles, which is that you want to occupy all the slots and you want to make as many objects as possible, entropy, then you get these things. And that's indeed what happens. And here you can see one of them where you see that indeed you can self-organize a unit which has 6 of those molecules, 9 connectors, which is what you need, 3 times C times 3, and they go together, you just mix and you get. And of course you can make them much more complicated. This has been done, and it shows, and of course many more complex objects that have been made, which 15 years ago people would not have dreamt of making. They would have said, you are crazy, it's not possible. But many groups around the world have made, by this process of self-assembly, very complex architectures of all types. Here is another one which sort of shows another type of object, a cylinder of nanometric size. A cylinder is defined by flat things and long things. At the ends, flat, and generators. Here, it's a cylinder where you have a red strand having 1, 2, 3, 4 points where you can link things together. And you have 1, 2, 3, 4 flat surfaces which can connect. So if you mix the linear molecules with the planar flat molecules, add to it the middle lines which will connect them, spontaneously you get this nano cylinder. 19 components go together spontaneously and just assemble and give this final object. This is just, as I said, an illustration, and the area of what you might call artificial self-organization has now enormously developed, and many groups around the world work in that field. For this area, very important for the DIPC, at least for some groups there, and many of them, of nanoscience and nanotechnology, of course we know that the fabrication of the objects, of the devices which are used in nanoscience and nanotechnology is the process by which we have been able to generate all these fantastic, powerful types of devices which make our computers, which are able, we heard about, also will maybe implement much more complicated things in quantum physics. But this is a fabrication way. You have to make these things. Self-organization makes you think that you might be able to let these objects assemble themselves. If you are able to control the type, the structure of the object, of the basic unit, the way they get together, rather than having to make it, you can let it make itself. So go from fabrication to self-fabrication. A way to convince you of that is to say that, for the moment, the most complex computer we have is, of course, the brain. This is self-organized. You don't have to make it. It makes itself. And the pieces it's made of are not nano, much bigger. So, nature, matter, has the properties to do it. So the question I can ask, there's a step beyond nanoscience and nanotechnology, which is complexity. And that's what we should strive for in the future. Not that it will put on the side the rest. The approach of building things up is very powerful. I want to insist on that. I don't want to give the impression that you have to discard it. Not at all. But you have to think about the possibility that there is this self-organization which can lead to the self-build-up. We saw that sentence a moment ago. There's plenty of room at the bottom. Sure, we knew it, and we saw it, and it has been brilliantly illustrated. But there's more room at the top. Now, the next step in these processes of self-organization, I cannot get into it, but I want to give you a flavor of what it is. What I have shown you by these few examples of these architectures which build up, the grids, the helices, the cylinders, is what you might say a way to design the system. You think about the brick, the molecule, you think about how it will interact with the cement, and if you understand what you are doing, and progressively you understand better and better, it will assemble finally the way it should assemble. This is design system. You design your system, you put in, so to say, the structural information, and you program it so that when it interacts with a given, in that case midline, the cement, it will lead to the final entity. But it would be very interesting that in addition to that, the system chooses what it needs and builds itself up by choosing from the diversity of objects around the ones it needs. And this is a self-organization with selection. This means, of course, that you need to have, you can have systems, if the system functions in that way. Your environment can have many different objects. But these objects will then be selected in this diversity of objects so that only the ones needed will be incorporated into the architecture you want to build up. For doing that, as is written here, you need diversity, many different objects, so that they can figure out and choose one or the other. And you need dynamics. You want things to get together, and if it is not good enough or not the best in the conditions in which you operate, to separate and try something else. This is dynamics. In other words, a world where things get together and stick is a dead world. You stick somewhere, that's it. But you have to be able to explore the energy hypersurface so as to find progressively the way which leads to the best assembly. This also opens a possibility and a step very important in at least that part of chemistry, which as you can set up systems which can adapt. In other words, and this I cannot give you examples, I have no time for that, but what it means is the following, that if you change the conditions in a system which is able to select from diverse entities, from diverse building blocks, it will change itself. It will adapt. For instance, you add water, or you add some acid, or you add another compound, and the system will adapt to the change which you have introduced. So this step is making systems adaptive, chemical systems adaptive. So this self-organization process, which is both at the molecular level and at the supramolecular level, which operates on both levels, is able to lead then, if you introduce this ability to select, to chemistry which is adaptive, later on evolutive, because if you want to evolve, you have to keep the information from the first step to transfer it and to build on the first one. Adaptive could say is something in equilibrium. You have a given system, and it will stick there. But if you want to go a step further, you have to freeze that and add new information and go further and further. And this then, indeed, gives to chemistry a sort of Darwinian flavor. Chemistry is getting into a state where the objects you look at are objects which can adapt to changes, not because you make them from the outside, but because it is able to change its components, its structure, its properties according to changes, like temperature changes or, as I said, medium changes or addition of other compounds. And it gives them a sort of a Darwinian flavor. Not to say that it's as complex as Darwinian evolution, which is much more complicated. But as I mentioned at the beginning, before the threshold of life, there was a purely chemical evolution. And there must have been a progressive complexification with a choice of given components, not necessarily a finalistic choice, but a choice which depends simply on thermodynamics and giving more and more complex objects. Until the complexity is reached, which we don't understand yet, to make something which we call living. But that will be done. So, self-organization represents the steps to complex matter. And what do we have to do? First, to describe. We look at biology, we look at viruses, we can try to see how it happens, and try then to understand how it happens. And when we understand better and better, then we can make use of it and hope that, thanks to the understanding of these processes by which complex molecular and supramolecular entities can build up, we'll go further and further towards complex forms of matter, from organized to living to thinking matter. This idea, in fact, is around for some time. Maybe not in the same context, of course. But nevertheless, Leonardo da Vinci already wrote a very strong sentence many years ago, where nature finishes to produce its own species. Many of you probably know Italian, so read the top. Man begins using natural things. We know what that is, the periodic table of Mendeleev, the elements which make up our matter, in harmony with its very nature. That's the laws of physics. You cannot go against the laws of physics. Without laws of physics, there's no chemistry. So, in agreement with the laws of physics, and they tell you what can do, what can work, what cannot work. And then comes the ending, which is a very strong ending, to create an infinity of species. Create an artistic, what an artist considers as his or her characteristic, creating something. Infinity, yeah, you can with the building blocks make an infinity of things. The number is not determined, the types is not determined, just some properties make it to fit together, but there's an infinity of possibilities, infinity of species. This is like art. And this gives also into chemistry sort of a power over matter. When Rodin made this sculpture, it was not contained in a stone. It is the artist which expressed out of the stone this sculpture. When Luis de Pablo writes music, uses sounds, and the music written is not in the sounds. It's the artist, the composer, who makes this. He creates it. When a novelist writes a novel using words, the words don't contain the novel. The novel is something created on the basis of the words. And in the same way, all these entities which are still to be made by recomposition of the elements which make up the universe are in the hands of the chemists to create all these molecular, supramolecular, and more complex objects which do not yet exist and await to be made. So the essence of chemistry is not just to discover. Of course, it's very important to discover. But the most I would say the most essential is to create novel expressions of matter. And you may call chemistry creative force, sort of an art of matter. Prometheus conquered the fire. That fire makes science. We cannot give it back. And there's another representation, and this one is a funny one because he just has stolen fire from the gods and is running away to bring it to the humans. And then he brandishes it. Our path leads us from the tree of knowledge to the control of our destiny. Now you excuse me for a moment. Not finished. So, passion for knowledge, the tree of knowledge, and the control of our destiny. Lucas Cranach is one of those middle-aged painters who painted lots of nice things. I like Cranach quite a lot. But they had something they liked to paint. Eve, and of course Adam also. But Adam is secondary for us today. Eve. What did Eve do? Here is Eve. Not bad. Nice looking. But she does something. What is she doing? What is she doing? Picking the forbidden fruit of the tree of knowledge. That's the birth of science. Ladies, the first scientist was a woman. Not finished. I have spoken a little, we have heard physics a lot, we have heard biology, I told you about chemistry, we shouldn't forget mathematics. And this person is of course one of the most famous mathematicians, David Hilbert. He's buried in Göttingen. On his tombstone he has a sentence which he wanted to be inscribed. What is this sentence? Wir müssen wissen, we must know. Wir werden wissen, we will know. From the tree of knowledge to the fire of science, we will know. Thank you for organizing this meeting, Passion for Knowledge. Thank you, Pedro.